Okay, welcome to yet another installment of the Bandwidth Theory Seminar. Our speaker today is Dr. Vishnu Narayan. Vishnu is currently a postdoctoral fellow with Professor Michal Feldman at the Tel Aviv University in Israel. And previously, he completed a PhD at McGill University in Canada under the supervision of Professor Adrian Vetta. And his main interests are on fair division and multi-item options. So today he's going to be speaking to us about these three specific techniques: quantiles, subsidies, and randomizations, and how they've produced recent advances in the theory of fair division. So thanks for coming, Vishnu, and over to you.
Thank you. That's a very nice intro. Yeah. Thanks for inviting me. Nice to see you all, some of you for the second time, maybe even third time. Yeah, so this talk, as the name and abstract suggests, it's going to be a sort of high-level fair division talk. I'm going to talk about a few of my recent results. This indicates three things, but I'll actually be going a little bit on a fourth thing as well. So this has quite a lot of fair division intro. Some of you may be very familiar with it, so I'll go through it a little bit quickly, but of course, feel free to stop me anytime and ask any questions in the middle. Yeah, so I'm a postdoc at Michal Feldman, and my research has been broadly in the intersections of like combinatorics, algorithms, game theory, and economics. So I was working originally on options, but about halfway through my PhD, I got interested in a conference talk that I saw on fair division. And since then, as you can see, all my recent work has been mainly in fair division, and that's what I'm currently working on right now. Shout out some of my co-authors for the papers that I'll be presenting today, and also some ongoing and future work. So I'll begin with quick intro to the fair division problem. Some of you may be familiar with this already, because Siddharth does similar things. So of course, it asks, how should a separate? It's a collection of problems that asks, how should a set of agents divide a collection of items among themselves in a fair manner? And there are many real-world applications of this. So there are many classical examples that you may think of immediately, like the division of inherited estates, public resources, something that may be closer to you, which is the fair division of seats in college courses. But there are also many modern applications, like the division of electromagnetic spectrum, airport traffic, computational resources, and there's hundreds of other things you can do. So depending on the sort of exact problem you want to solve, there are many formalizations you can make for the question in the first line, which leads to different problems. But generally, when we're talking about the fair division problem, we abstract all of that away and look at the following picture, where we have a collection of agents that want to divide a set of items among themselves. Here I have some office supplies, and we want to assign the office supplies to the agents such that everyone gets some bundle and all of the items are assigned. And we want to do this, of course, as the name suggests, in a fair manner. So that brings us to the obvious question of what does it mean for an allocation to be fair? And the collection of fair division problems tries to come up with definitions of fairness that mirror our intuitive understanding of what it means to be fair. And then you can ask questions like, does a fair allocation always exist, and can one be efficiently computed? So if you think about this for a moment, you'll realize that when you have divisible items, then it's known that fair allocations exist under mild assumptions on the valuations, and that they are computable in some query model. And also, if the agents have identical preferences over the items, then you can just have that one agent finds a suitably fair partition for your definition of fairness and assign those bundles arbitrarily. So the hard case is the remaining case, where you have indivisible items and you have varying preferences. So generally, for this case, which you want to study, there are a lot of definitions of fairness for which it's not known whether fair allocations exist and whether we can find them. So that's what I'm going to be talking about today. And I'm going to use this example as a running example over the next few slides for multiple papers here, where you have three people, Alice, Bob, and Charlie, and they want to divide some 4 items: the desk, the chair, the pen, and the laptop among themselves. And now we have to find some way of expressing how the agents have different preferences over these items. And we do that with, of course, valuation functions. So given an instance with n agents and m items, every agent I has a valuation function that assigns a value for every subset of these items. Right? So we make some very minimal assumptions on these valuations, that they are normalized, which means the value of the empty set is 0, and that they are monotone, which means if you keep adding items to an agent's bundle, that agent's value for the bundle is going to weekly keep increasing. Now, on top of these very small assumptions, there's a lot of additional assumptions you can make on the structure of the valuation. For many of these talks, I'm going to just have these assumptions and call these monotone valuations. But you can impose some additional structure. For example, you can say that the valuations are additive, which means every item has a value, and your value for a set is just the sum of values for the items. You can also have, like, for example, unit demand valuations, where the value of a set is the maximum of the values of the items. And there's a lot of other structure you can impose on the valuation functions, which gives you a lot of valuation capacity. I suppose in valuations that are defined on n items, where you have n agents and n items, there's not really. Well, zero valuation, where everything is valued at zero. There's intersection. Yeah. It's you can come up with some trivial valuation for them. Yeah, so there are a lot of other valuation classes. The exact details are not really important, but they have this sort of hierarchy, and this is very widely studied in economics. It's called the complementary hierarchy. Of course, I've included a couple of extra valuations here, and this is widely used well beyond fair division, even for the study of auctions, contracts, etc., where subadditive valuations, the widest class, just says that the value of the union of two sets is at most the sum of the values of the sets. And on top of that, you can impose any of a bunch of additional structure to get any of these other valuation classes. And if you're making additional assumptions on top of monotone valuations, typically you want to study valuations in one of these classes in fair division. Okay, so with that, we've of course arrived at the main question of what does it mean for an allocation to be fair? The fair division has been studied since the 1940s, so for many decades now. And over the years, people have come up with many definitions of fairness, but you can categorize all of these definitions into two broad classes pretty naturally. One of them is fairness by comparison, where an agent compares its bundle with the bundles of the other agents. And the other is fairness via shares, where there's some shared function that assigns a threshold for every agent after looking at its valuation. And an agent assesses a bundle as fair if the value of the bundle is at least that threshold. So I'm going to be talking in this talk about 4 of my recent papers. 3 are published, and 1 is a working paper, ongoing work. 2 of them are about fairness by comparison, and 2 are about fairness via shares. So I'll start with the fairness by comparison side. And if you have any questions, please feel free to stop me again. So the first part about envy. As you may know, sort of canonical fairness definition in the fairness by comparison category is envy freeness. And as the name suggests, an allocation is envy free or free of envy if no agent envies anyone else. So each agent's value for its own bundle, VI of AI, is at least its value for every other agent's bundle, which is VI of AJ. And if this is true for all pairs I and J, the allocation is envy free. Now, when the items are divisible, it's known that envy free allocations exist with very mild assumptions. But if you take the same definition of fairness and apply it to indivisible items, let's look at what happens. So we have our example from before, and I'm going to assume now the agents have additive valuations and fill out some numbers here. So an agent's value for any bundle here is just the sum of these numbers. As you can see, the agents sort of unanimously agree that the laptop has very high value, right? So any agent that gets the laptop is going to be envied by some other agent, no matter what they get, because the laptop has much higher value. So of course, in this example, envy freeness is impossible. There is no allocation that is envy free. So what happened was this led the community to, once they started working on indivisible items, to define some relaxations of envy freeness, where we allow for some envy because envy is inevitable, but we bound the amount of envy. The first famous one is called EF1, which is envy free up to 1 item, where envy is allowed but bounded by the value of some item, which means there exists an item G in AJ such that VI of AI is at least VI of AJ minus G. Looking at our example from before, this is in fact an EF1 allocation. So there is a very high valued item, the laptop, and Charlie gets the laptop. But Bob and Alice don't EF1 envy Charlie because when they're making their comparison to Charlie's bundle, they're going to hide the laptop because they're allowed to hide one item. And when Bob and Alice are comparing with each other's bundle, Bob does not EF1 envy Alice because Bob can just hide the desk. And Bob prefers the pen to the chair. So this allocation is in fact EF1. Okay. So this is not an accident. It's not just true for that additive example I gave you, but it turns out that EF1 allocations exist for all profiles of monotone valuation, which is the widest class we're considering without any additional assumptions on the structure. This is a very famous result of Lipton, Markakis, Mosul, and Saberi from 2004. And it uses a very famous and very simple algorithm called the envy cycles procedure. I'm going to give you a quick description of this algorithm because I'm going to talk about it again in more detail for one of the papers I'm presenting. So how does this work? Suppose now, forget about the table of valuations and just suppose that Alice, Bob, and Charlie want to divide these office supplies among themselves. So we're going to look at, so what this envy cycles procedure does is it assigns the items one at a time. And every time it assigns an item, it gives it to an agent that nobody envies. So initially, all the agents have nothing and nobody envies anyone. So we can just pick Alice and the scissors, give Alice the scissors. But now this would cause Bob and Charlie to start envying Alice. Right, so nobody envies Bob, so Bob can get the next item, which is the books. And this causes Charlie to envy Alice and Bob, and also Alice to start envying Bob. And now, suppose nobody envies Charlie, so we give Charlie the pen, and Alice and Bob start envying Charlie. But at this stage, nobody envies Alice now. So we're going to just give the next item to Alice, which is the desk. But now suppose Charlie starts envying Alice, but nothing else changes. So you can get stuck in a situation where Alice envies Bob, Bob envies Charlie, and Charlie envies Alice. But now it's a very easy fix. You can just take the three agents' bundles and shift them back by one agent along the cycle, and that removes all of those envy edges, right? Because they're all now getting the bundles that they envied. And now you're creating new source vertices in this graph by doing this, which is new agents that nobody envies. And you can continue assigning the remaining items and so on. So when you're done, that's the final allocation. And it turns out that if you think about this for a moment, it's very easy to see that this is in fact EF1. It satisfies the condition we saw earlier, because anytime an item is being given to an agent, nobody envies that agent before that item is assigned. So that's exactly the EF1 condition. If anybody is comparing their bundle with that agent, you can remove the last item that that agent got, and the envy is removed. So this is EF1. And this extremely simple algorithm proves that EF1 allocations exist when the agents have monotone valuations with no other structure. With that, that was the start of a very major research program in fair division, which was to combine EF1, which we now know exists for monotone valuations, with other desirable properties like high social welfare or Pareto optimality or other fairness notions. And there's a lot of papers. In fact, there's like hundreds of publications now in the last 20 years, which tries to do this, tries to show that you can combine the EF1 property. You can always, for every instance, find an allocation that is EF1 and also has some other desirable properties. And usually these are for the structured valuation classes we saw on the previous slides. But is that the end of the story for fair division? Of course not. Are we actually satisfied with EF1? And most of the fair division community argues that this is not a very good fairness definition because it allows for some very bad allocation. So in the same example we had before, if we have this other allocation instead, where Alice gets the chair and the laptop, this is also EF1. So despite the fact that Alice gets the highest valued bundle here, the unanimously highest valued item, the laptop, you can give Alice another item, the chair, and nobody envies Alice after hiding the laptop. So this is in EF1. In fact, if you had a bunch of small items, you can give them all to Alice as well, and it will still be EF1. Right, so this is bad. And there's a few things you can do about this. The first thing that you can try to do is find some way to augment EF1 with some sort of stronger fairness guarantee that is some version of envy freeness. And there are sort of two directions in which to do this, which are subsidies and randomization. And there was a line of research in both of these directions. And I'm going to be talking about two recent papers, one on each of these topics. All right. So the first one is fair division with subsidy. As the name suggests, it has something to do with subsidizing the agents or using money in some way. So the famous Nobel Prize winning economist Maskin, he asked in some classical work now, whether we can bypass this envy freeness impossibility by adding something that he called a small divisible good akin to money into this fair division instance. What does this mean? We're going to call an allocation A envy freeable if it can be made envy free with some payment vector. So there exists a payment vector P such that AP is envy free. That means VI of AI plus PI, which is agent I's value for its bundle AI, plus agent I's payment PI, is at least VI of AJ plus PJ, which is agent I's value for J's bundle plus J's payment PJ. Right? And if this, yeah. So agent J gets the bundle AJ plus the payment PJ. Agent I gets the bundle AI and the payment PI. And you want that I does not envy J's bundle plus payments. I is going to compare I's bundle plus payments with I's value for J's bundle plus payments. So the sort of economics assumption here is that the agents have what are called quasi-linear utilities, that everybody has the same value for money, and their value for the bundles can be expressed in some linear way against the money. So you can just add the payments on both sides of that inequality from before. Yeah. So Maskin, in fact, showed that in the special case where you have n agents and n items with some standard normalization where you just scale all the values down such that the value of an item is at most $1, an envy freeable allocation always exists. So this normalization is just to make it easy to talk about the results. So what we're going to do is we're going to try to talk about how much money we need to make an allocation envy free. And we're going to do it in terms of dollars. So dollar just means the maximum value of an item. And Maskin also showed that at most n minus $1 with that normalization suffice to eliminate envy. And this is tight. So notice that this is not front. It's not obvious that this is possible, right? Because we're giving payments to the agents, but also the payments are taken into account when you're looking at the NV. So you want to give, like, if you pay one agent, that's also increasing the other agent's NV towards that agent. It's not just decreasing that agent's NV towards everyone else. So let's look at an example from before. So this was the instance with the EF1 allocation. Can we make this NV free with payments? So now, of course, Charlie gets the highest valued item. So you want to start by eliminating Alice's NV towards Charlie. So Alice values the laptop at 300 and her own bundle at 100, 50 plus 50. So you need to give Alice $200 in this example to eliminate her NV towards Charlie, right? And if you look at Bob's NV towards Charlie, Charlie is okay with Alice getting $200 here because Charlie has very high value for the laptop. But if you get Bob's NV towards Charlie, Bob values the pen at 40 and the laptop at 600. So you have to give Bob 560. But now, of course, Charlie has a problem with this because Charlie would rather get the pen plus $560 than just the laptop at $400. So what can you do? If you give Charlie more money now, Bob will continue envying Charlie and so on. So you're stuck with this. And this allocation, in fact, can't be made envy free with payments. So let's look at this other allocation. Charlie instead gets the desk and chair. Alice gets the pen and Bob the laptop. So now, to remove Charlie's envy towards Bob, you need to give Charlie $270, which is 400 minus 130. And this is fine. Bob's okay with this. To remove Alice's envy towards Bob, you need to give Alice 300 minus 20, 280, right? And now this removes Alice's envy towards Bob. But notice that in this example, Alice still envies Charlie. Alice would rather have the desk, the chair, and $270 than the pen and 280. So to get rid of Alice's envy towards Charlie, we need to, in fact, give Alice, there's a higher lower bound on the amount of payment you have to make towards Alice, which is 350, which is Alice's value for Charlie's bundle, minus Alice's value for Alice's bundle. So this, in fact, is an envy-free allocation with payments. So this allocation is envy-freeable in the sense that for every pair of agents ij, every agent prefers its bundle plus payments to any other agents. But the underlying allocation here, okay, we'll get to that in a moment. So for the general M item case, there was a line of work that showed the existence of envy-freeable allocations for all instances. So even without this additive instance assumption, and when the number of items can be anything, not necessarily n, there is always at least one allocation that can be made envy-free with payments. But as we saw in the example, not every allocation can be made envy-free with payments. But if you look at this example here, the underlying allocation without the payments is quite bad, right? So it isn't EF1. I mean, it isn't even EF1 because Alice has just one very low valued item, the pen, and Charlie has two high value items, according to Alice. So Alice EF1 envies Charlie. So this raises a sort of obvious question. Two questions, in fact. They were both asked as conjectures in the work of Halpern and Shah. So they conjectured that for additive valuations, the first is that the bound from the original work of Maskin applies not only for the n item case, but more generally for m items when you have additive valuation. So at most n minus $1 suffice to eliminate envy, where recall that $1 is the maximum value of an item. The second conjecture was that there is always an allocation that is simultaneously envy-freeable in EF1. What this means is for any instance with additive valuation, you can find an allocation that is envy-freeable. I mean, sorry, that is EF1, and for which you can add some payment vector to this allocation and make it envy-free. So these are the two conjectures, and this was the paper I saw at a conference in 2019 that got me interested in pair division. So our first result in pair division was that this is actually possible. So we proved both of these conjectures, and we showed that with additive valuations, in fact, we showed something a bit stronger. We proved both of them with one algorithm that has some additional properties. So there's a polytime algorithm that finds an allocation that is simultaneously EF1 and envy-freeable, whose subsidy is at most $1 to each agent. So at most n minus 1 in total. So how does this work? If you look at our example from before, we had this process where we were looking at the graph of envy on the agents, right? So we can formalize this in the following way. You instead have this complete directed graph where the agents are the vertices, and you have an arc for every pair of agents. And you're going to add some weights on an arc. So every allocation gives you a weighting function on this graph. So the weight on the arc ij is vi of aj minus vi of aj, which is agent i's envy towards agent j. Yeah. Yeah, so if you take any fair division instance, you can just assume you're scaling all the valuations down uniformly for all the agents until the value of an item is at most $1. That's all we're saying. Yeah, that wasn't the case. Yeah, just imagine you divide this by 600 everywhere. Sorry, should have probably done that. I mean, I'm using large numbers to make it easier to think about. Yeah. So, I mean, here the phrase $1 just means you can just replace it in your head with marginal value of an item. It's just to make the amount of money easy to express. Okay, so look at this complete directed graph and this weight function. And there is this characterization in the literature. In fact, it's shown up independently in many different words. It says that an allocation is NV-freeable if and only if this directed graph with these weights has no directed cycle of positive total weight. In other words, this is called local efficiency. So an allocation is NV-freeable if and only if it's locally efficient, which means there's no way that the agents can rotate the bundles among themselves, the fixed bundles, on any cycle and increase the sum of their values. If this is true, the allocation can be made NV-free. And notice that since you have no directed cycle of positive total weight, the heaviest path starting at every vertex is well defined in this graph. Because if you had a positive weight cycle, the heaviest path is not going to be well defined. You can keep going around that cycle and increasing the weight of your heaviest path starting at every vertex, right? But with no positive weight cycle, the heaviest paths are well defined. And a feasible payment vector is just for every agent is just the weight of the heaviest path starting at that vertex in this graph. Yeah. Yeah, you can. You would never repeat vertices because if you have no positive weight cycle, you don't want to go back to the same vertex. Yeah. All right. So as I said, the minimum payment to I is the weight of the heaviest path. It should say starts at vertex I. Sorry. Max over all paths, weight of the path starting at I. Yeah. So with that, our algorithm is actually extremely simple. It's just a repeated maximum weight matching. So you first add some dummy items to make the number of items a multiple of the number of agents that have value 0 for everyone. So I'm going to add the item 6 here. And then I'm just going to repeatedly compute a maximum weight matching between the agents and items. Here, Alice gets 1, Bob gets 5, and I'm going to assign those two items. And then compute another maximum weight matching where Alice gets 2, Bob gets 4. So notice that this is the maximum weight matching. It has value 0.8 plus 0.7, which is the heaviest matching in this example. Right, and we assign these two items and then find the next matching, assign the items and so on. So the final allocation is Alice gets 1, 2, 3, Bob gets 4, 5. So the heaviest part was just the characterization. It said an allocation can be made NV-free with payments if and only if there is no positive weight directed cycle. And then given an allocation that satisfies this property, you can easily compute the payments by finding the heaviest part starting at every vertex. This is the payment function that makes the allocation NV-free. Now, what are we trying to do? We're trying to show that there exists an NV-freeable allocation satisfying additional properties. One is that it's EF1. Two is that the payments are at most something. So we have an algorithm that finds an allocation that is NV-freeable and EF1, and the payments are at most something. This is the algorithm that computes the allocation. And later, we're going to prove the properties. Right. So the first thing we want to prove is that this allocation is NV-freeable. The second is that it's EF1. It turns out these two are extremely simple, but already this resolves the first conjecture of Halpern and Shah. The third is that the subsidy is at most 1 per agent or n-1 in total. And that's the really hard part here. I'm not going to go too much into the details. The NV-freeability is very easy to see. So by the earlier characterization, we want no positive weight directed cycle. But because we're doing a maximum weight matching, we get this sort of immediately. Because if you had a positive weight directed cycle in the final allocation, then the weight of a cycle in the final allocation is just the sum of the weights in each of these maximum weight matchings. So if you had a positive weight cycle at the end, you have a positive weight cycle in one of the maximum weight matchings, which is a contradiction. So that gives you a matching of higher total weight. That's it. So that is NV-freeable. Now the allocation is also EF1. It's also very easy to see. It's similar to the proof that round robin is EF1, if you're familiar with that. So each agent weakly prefers the item that it gets in round T to anyone else's item in round T prime, for any T prime greater than T, right? Because in each step, we're computing a maximum weight matching, and T prime is available. The item that an agent gets in T prime is available in round T. So any NV from I to J is eliminated by hiring J's first round item. And the allocation is, in fact, sorry about that, is EF1 as well. So the harder thing to show is that the subsidy is at most 1 per agent, or n-1 in total. Now, in the interest of time, I'm not going to go too much into detail here, but basically, what you want is, notice that we know that if A is EF1, then the weight of any arc ij is at most 1, right? Because we said the value of an item is at most 1. And if your NV is bounded by the value of one item, then the weight on any arc is at most 1. But this just tells us that the weight on any path is at most n, not at most 1. The weight on, and specifically the weight on the heaviest path starting at every vertex is at most n. So if you want that the weight on the heaviest path starting at every vertex is at most 1, one way to get this is by having this additional property. So just as a thought experiment, just imagine that the weight on any arc, instead of in addition to being at most 1, it's also at least -1. If this were true, what would you have? In conjunction with this, you also have no positive weight directed cycle. That would give you that the maximum subsidy is at most 1 for every agent. Because if you look at this simple proof by picture, you have the arc from I to k, whose weight is at least -1. So every path from k back to I has weight at most 1, because otherwise you have a positive weight directed cycle here. Right? So if you had the property that the weight is at least -1 and that there's no positive weight cycle, then the weight of every path, including the heaviest path starting at every vertex, is at most 1. But of course, you can't get this property. So -1, so the weight of ij being in between -1 and +1 implies that all agents are sort of almost indifferent between all of the bundles. And such an allocation, I believe such an allocation doesn't exist. It's a sort of corollary of some discrepancy theory stuff, but I'm not 100% sure. But at least our algorithm doesn't find such an allocation. So one trick now is to consider a carefully constructed alternate instance with valuations v bar for every agent I instead of v. So I'm not going to explain exactly how like the definition of v bar, but the idea is that given an instance, you run this iterated matching algorithm. It gives you an allocation, and you want this certain property that the weight of any arc is at least -1. So we're going to take that allocation. We're going to construct a new valuation function v bar for which that property is true. So then what do we want to show? The allocated output by the iterated matching under v is still NV freeable under v bar. Then we want to show that the minimum payment is at most $1 per agent under v bar, and therefore for v bar we are done. But then the minimum payment under v is at most the minimum payment under v bar. This sort of using the alternate valuations v bar as a tool to prove the bound for v is something that we introduce. And without going into too much detail, it helps us prove this conjecture. So we presented a simple algorithm and the new proof technique, which is the reduction to the alternate instance. So our new techniques led to many new results on fair division with subsidy, and there's been a huge amount of follow-up work in the last 4 years on this topic. The payments are easy to compute. So like I said, given an allocation, it's easy to compute the payments. It's just the heaviest path starting at every vertex. Yes. Yes. With the iterated matching thing. That's what we do. Yeah. So the algorithm, extremely simple, is just the repeated matching. And if you assume that the value of every item is at most 1, you also have the property that the weight of every path is at most 1. Now, proving that the weight of the heaviest path is at most 1 takes a bit of work. Okay. So that was the work that sort of closed this question for additive valuations. But we also show that for monotone valuations with no other structure, there is a polytime algorithm in some Oracle model that finds an NV freeable allocation whose subsidy is at most O of n squared. So we still have the n-1 lower bound here, and this leaves some questions open. So primarily, can you find tight bounds for monotone valuation? So after our work, there's been a lot of work for other structured valuation classes that shows an n-1 bound on the payments, but that question is still open for submodular functions, for subadditive, and more generally for monotone valuation. Okay, so that's the end of the discussion on subsidy. I'm going to move on to the second topic, which is fair division with randomization. Are there any questions about the previous part? I think I've already answered most of your questions, but okay. The second topic, as I said, was can we get to some version of NV freeness on top of EF1 in a different way? So one way you might want to do this, you might think about doing this, is can you use randomization to help you? And we're going to call a random allocation fair ex ante and use the orange color if it is fair in expectation, and call an allocation fair ex post with that purple color if every allocation in the support, every deterministic allocation in the support of this random allocation is fair. So on its own, suppose we wanted to get to NV freeness with randomization. So we want to have NV freeness in expectation. On its own, ex ante EF is trivial. If you think of any way to do this, you have 3 agents and a bundle of items. You can just give the items, all of them, uniformly to one of the agents with probability 1 over n. And this is NV free in expectation, because everyone's random bundle is the same. They get everything with probability 1 over n and nothing with the remaining problem. But of course, for every deterministic allocation in the support, it's horribly unfair because one person is getting everything, right? So it can lead to very high unfairness exposed, which leads to an interesting question, which was asked by Aziz in 2019. Do there exist random allocations that are ex ante EF and ex post some version of relaxed EF like EF1, which he called the best of both worlds? So if you randomly assign a bundle, it's envy-free in expectation, because each agent's expected value for its bundle is 1 over n times its value for everything, which is exactly its expected value for anyone else's bundle as well, because they have the same random bundle. I mean, after the randomization is realized, for any positive probability allocation, for example, this allocation where Alice gets everything occurs with probability 1 over n. It's a deterministic allocation in the support of the random allocation, and it is extremely unfair. So, right? So this asks, can you get ex ante envy? Can you find an allocation that is ex ante envy free, but also has some exposed fair properties? Or in other words, given and fair division instance, there is a collection of EF1 allocations, right? In each EF1 allocation, you have some amount of envy, like I envies J, for example. But is there also some other EF1 allocation where I greatly prefers its own bundle compared to J's bundle? And there's some way to assign probabilities to all these EF1 allocations such that in expectation, you're envy free. Is it possible to do this for all instances is the question. Yeah. Yeah, that's true. Yeah, you can just, I mean, if you wanted to find an ex ante EF1 allocation, you can just take a single deterministic EF1 allocation, which is also ex ante EF1. But you want to get ex ante envy freeness, and you know that envy freeness doesn't exist for most instances. Yeah, I don't think anyone has thought about that, but you can say something like maybe you can get stronger properties if the total probability of having the total mass of EF1 allocations is at least 1/2, something like that. Yeah. Yeah, that's, I don't think anyone's thought about that. Yeah. More a question of, this is more a structural question of, given an allocation, how are the EF1 allocations distributed in the NV space, right? If you take the collection of EF1 allocations in the space of NV, where every axis is the NV that one agent has towards another agent. So you have this n square dimensional space. If you take the set of EF1 allocations, does the convex hull contain a point in the positive orthant, which is NV free in expectation, like the fractional allocation? Yeah. Okay. So this was actually answered 1 year later in 2 independent works of Riemann, Shah, and Weiss, and also by Aziz. And they showed that the natural result actually works for additive valuations. So when the agents have additive valuations, there exists a random allocation that is ex ante envy free and ex post EF1. This led to a lot of interest in this topic and many follow-up works that all show EF and EF1 for other structured valuation classes. But these are all interesting, but they're all limited in the exact same way. So they are very structured classes with about as much structure as additive valuation. And also the exposed guarantee is EF1, which we saw is somewhat weak, right? So one question you can ask is, can you do better than EF1? And can you do this for broader valuation classes with less structure? So this do better than EF1 leads us to our second relaxation, the famous EFX relaxation of envy freeness. Recall that an allocation is EF1 if the NV is bounded by the value of some item. There exists a G in AJ such that VI of AI is at least VI of AJ minus G. To get to EFX, we just change the quantifier to any item. So there exists a G in AJ such that VI of AI is at least VI of AJ minus G for all G in AJ. Sorry, instead of there exists. Or in other words, the NV is bounded by the value of the smallest item in the other agent's bundle rather than the largest item. Because if an agent is going to hide an item from the other agent's bundle before doing comparison, can you make it hide the smallest valued item rather than the highest valued item? So this, what can we say about EFX now? Looking at our example from before, this EF1 allocation is not EFX because now if Bob compares its bundle with Alice's, Bob would hide the chair and not the desk. And Bob has very high value of 60 for the desk. So Bob EFX envies Alice. But this other allocation, Alice gets the desk, Bob gets the chair and pen. This is in fact EFX because Alice and Charlie get only one item, so no one EFX envies them. Bob gets 2 items, but Alice can hide any one of those 2 items and will not envy the other item. Right? So this is EFX. Does this always exist? This is the biggest open problem in fair division. It's widely considered to be the biggest open problem, and it's surprisingly extremely open. There is no existence proof of EFX allocations, even for additive valuations, and there is no counterexample, even for monotone valuations with no other structure. This is a really big, really interesting, and fully open problem in fair division. But you can still make some other theorems about EFX allocation. So that's what we try to do. So can we do better? One question is, can we extend all of this best of both worlds work beyond additive valuations all the way to subadditive valuations with the least amount of structure? And the other question we can ask is, can we get ex post EFX instead of EF1, the stronger fairness guarantee? So we know already that the ex post EFX question is in fact still open, but our first result is an impossibility. So with subadditive valuations, simultaneous ex ante EF and ex post EFX is impossible. So there is no distribution over EFX allocations that is envy-free in expectation, even though we don't know whether EFX allocations always exist. So this necessitates the use of some sort of approximation, which is what we do to get a positive result. So with subadditive valuations, simultaneous ex ante 1/2 EF and ex post EF1 and 1/2 EFX always exists. So this is a more general setting than the previous work for additive valuations, and also it's a stronger ex post guarantee. So it's not just over EF1 allocations, but over EF1 plus 1/2 EFX allocations. So there is a distribution over allocations with a very strong ex post fairness property that is ex ante 1/2 EF. And this is tight in two senses, right? We already showed in the previous slide that removing both approximation factors is impossible, but also going beyond subadditive and removing all of the structure is also impossible. So for general monotone valuations, you cannot get any alpha EF and beta EFX for any positive alpha and beta in this best of both worlds. Yeah. Yeah.
EF allocations also EFX.
Yeah.
Also be exposed to EFX, right? So I don't quite understand what this is trying to say.
Yeah. So given an instance, we don't know whether. Sorry. For most instances, EF envy-free allocations don't exist. Right. So yeah, we don't know whether EFX allocations always exist. Specifically, we don't have a counterexample. But this is just saying we have an example for which there is no distribution over the EFX allocation. That is ex ante EF. Yes. Yes. Okay, so how we showed the half EF and half EFX thing is with the NV cycles that I showed you in the beginning. So there is a variation of the NV cycles algorithm. If you do something on top of NV cycles, you don't just get EF1, but you get EF1 and 1/2 EFX exposed for subadditive valuations, right? So the thing that we're trying to do here is try to find a way to randomize this NV cycles algorithm to give some ex ante fairness guarantee, some fairness and expectation guarantee as well. So we introduce a new sort of random distribution over the cycles of an NV graph in order to do this. So remember how the EF1, the NV cycles procedure work is that you want to keep assigning the items one at a time to the agents. And at some point, if you're stuck, then there exists a cycle in the NV graph, and you want to shift the bundles back by one agent along the cycle to create new source vertices. So that's the stage at which we want to do the randomization. So if you're stuck and an NV graph has no source vertex, then instead of selecting a cycle arbitrarily, as the NV cycles algorithm prescribes, you now select a cycle with some probability distribution to get ex ante NV cleanness. So specifically, you want to select a cycle with a distribution that satisfies this K probability. So if two agents I and J both envy some agent K, then they are equally likely to get the bundle AK. So how this works is you're selecting. Remember, you're selecting cycles with the probability distribution over the cycles. So the probability distribution over the cycles also induces probabilities on the edges. And what we're saying is if two agents I and J both have an edge towards K in the NV graph, then the probabilities on those two edges are equal, given the probabilities on the cycles. And how do we do this? So if you're given an NV graph that has no source vertex, then there is some strongly connected subgraph. We take that subgraph, take the transpose of the subgraph, and find its stationary distribution. In this example that I have here, the stationary distribution is given on the vertices. And then there's this work from McQueen in 1981 that shows how to decompose, given the stationary distribution, shows how to decompose this distribution into cycles over the edges, such that the cycles all have equal probability. And so such that the weight of any of two arcs going into the same vertex is the same in the cycle distribution. So we use that result, but what we're saying is if you select and when you want to during the NV cycles algorithm, when you want to eliminate NV by rotating along the cycle, if you select cycles with that probability distribution given by this result, then you get x ante 1/2 EF. It takes a lot of extra work to show the x ante 1/2 EF. You need to look at all of the tree of all possible random choices and show that for any pair of agents I and j, I does not envy j by more than a factor of 2 in expectation to get the x ante 1/2 EF. So again, I'm not going to go into too much detail, but this does leave a couple of open problems that I'll talk about in a moment. Sorry, was that a question? Yeah. It's the standard definition of stationary distribution in Markov chain. So we're going to take the strongly connected graph, flip all of the edges, and from a vertex, you have a bunch of outgoing edges, and you have equal transition probability. You divide your probability of one over the edges uniformly. Yeah, because what you want is that you have equal probability of. So if two agents envy the same agent, they have one. You want them to have equal probability of getting the bundle. So if you flip the two edges, that's like looking at a Markov chain where if you're at this state, you have equal probability of going to that state or that state, which is equal probability of those two agents getting this bundle. And with that, given that Markov chain, there exists a distribution. There exists a decomposition into cycles that satisfies that probability. Yeah. Okay, so that's the end of the discussion on the first part, fairness via NV. I'm going to talk about the second part now, fairness via shares. So as I said in the beginning, in fair shares, an agent doesn't compare its bundle with the bundles of the other agents. In fact, an agent doesn't care what the other agents gets, but there is some share function that assigns a threshold value for every agent. So the share function assigns a personalized threshold, which is called the share, to each agent. And an allocation is fair if everyone gets value at least their share. So there's a huge amount of literature on fair shares, but the definition of a share was formalized in this way very recently in this really great work of Babayoff and Feiger. Yeah, so there is a share function which takes as input a valuation and the number of agents and outputs a threshold. So the function is defined for all valuations. So the function maps from the valuations on the number of agents to some threshold. I'll give you some examples. One famous example is the proportional share. So the proportional share prop of vi comma n is vi of all items m divided by n. So the proportional share is just an agent's value for all of the items divided by the number of agents. So it's any function that just takes the valuation function and also the number of agents and outputs some threshold. And now the natural question you want to ask is about feasibility of share functions. You have this really rich definition of all possible functions that map from valuations to thresholds. Which of these is feasible in the sense that for that share function, if you have an instance, a bunch of agents show up to this instance, and the share function defines a share for each of these agents, can you always find a partition of the items and an assignment of the items to the agents such that everyone gets a value at least their share? So the fairness comes from the feasibility. So we're going to call a share function feasible if there's always, for every instance, there's some way to give everyone at least their share. So an allocation that gives everyone at least their share is a fair allocation. That's the definition of fairness we're using with fair shares. Of course, the zero share function is feasible. Yes, so no. I mean, you can't take like the identity of the agent into account. You have to, it's maps from valuation functions and the number of agents to thresholds. So if two agents have the same valuation function, they get the same threshold. Yeah. Yeah. So you can have trivial feasible share functions like the uniformly zero share function. But the question is, where is what is the characterization of feasible share functions? It's actually an extremely complicated question because the definition of a fair share is very rich. And we know a few theorems about the class of feasible fair shares, but we don't know everything about them. So that's the sort of thing we want to explore when we study fair shares, fair division. So some popular shares are this proportional share was defined by Banach, Master, and Steinhaus in the 1940s. For the divisible items case, where you can see with very mild assumptions that a proportional allocation always exists. But of course, with indivisible items, what can we do with this? Looking at our example from before, Since you have a very high valued laptop and everybody agrees that the laptop's value is very high, this also drives the value of the proportional share to be very high. And any agent that doesn't get the laptop is not going to meet its proportional share, right? Or at least both of the agents that don't get the laptop cannot simultaneously reach their proportional share. So the prop is in fact an infeasible share, even for additive valuations. And not only that, no positive fraction of the proportional share is feasible, because you can just take the value of the laptop and increase it to infinity, and anyone that doesn't get the laptop is getting a zero fraction of their proportional share. Right? So let's look at some other fair shares, and you'll see that they all have the same problem, the fair shares in literature. So the maximum share was defined as a relaxation of the proportional share. It's the maximum overall partitions of the minimum valued bundle in a partition. So what does this mean? You can think of the following like thought experiment that each agent does. So suppose each agent is going to partition the items into n bundles, and that agent thinks an adversary is going to pick a bundle for that agent. Right? So the agent is going to imagine that it's going to get the lowest value bundle. Then it would select a partition that maximizes the value of the lowest value bundle. So Budish defined the maximum share in his work in 2011, but left open the question of whether it's a feasible share for additive valuations. And it was shown 3 years later that it's infeasible even when the agents have additive valuations. So because every agent may have a different maximum partition, it's not possible to give everyone value which is even the lowest bundle in their maximum partition simultaneously for every instance, which is a sort of surprising result. So this, they also showed that something like a 2/3 fraction of the maximum share is feasible. And this led to a huge amount of work on this topic. So constant fractions of the maximum share are in fact feasible. And then in fact, about 100 publications showing that constant fractions of the maximum share are feasible for a variety of valuation classes and for different constants. But once again, as soon as you go to monotone valuations with no other structure, you can very easily see that no positive fraction is feasible for monotone valuations. Now, I haven't put the example on the slide, but it's a very simple example. There are many other shares in the literature, the any price truncated proportional share. They again all have the exact same property. They make sense for additive valuations, but as soon as you remove that structure, the share definition doesn't make a lot of sense because no positive fraction is of any of these shares is feasible. And if you contrast this with the NV-based fairness, where we know that EF1 allocations always exist for monotone valuations, we know that epistemic EFX, which is a different fairness notion, always exists for monotone valuations. And for all we know, maybe even EFX allocations always exist for monotone. So we have all of these share definitions, these fairness definitions in the comparison side, which makes sense, right? And you can try to augment those with additional properties for monotone valuations. But we don't have something similar for shares, which raises an obvious question. Is there a feasible notion of a share that is a reasonable notion of a share that is feasible for monotone valuation? This is one question we tried to answer in the recent work. We call this the quantile share. And this is based on two sort of very simple ideas. The first is to use the uniform random allocation as a benchmark for fairness. And the second is to measure fairness on the quantile scale rather than the value scale. What does this mean? Consider the random allocation that gives each item to any agent independently with probability 1 over n. So the simplest sort of random allocation you can think about. Take each item and give it uniformly to one of the agents. Or in other words, you have n to the m possible allocations. Select an allocation uniformly from the n to the m possible allocations. These are equivalent processes. And we're going to let xi be the random bundle of agent I in this random allocation. And the idea is that agent I is going to compare its deterministic allocation that it gets in an actual instance to this random allocation xi. And we define the Q quantile share, a parameterized share notion, in the following manner. So for every Q in 0, 1, the Q quantile share tau sub Q is the Q quantile of the random variable Vi of xi, agent I's value for its random bundle xi. What does this mean? It's a value for which a Q fraction of the values are smaller than this in the random bundle xi. So in other words, agent I asks, what is the probability that its given bundle is valued at least as much as the random bundle xi? And it's going to call an allocation fair if this probability is at least Q. The allocation is Q fair now for all the agents if this probability is at least Q for all the agents I simultaneously. Does that make sense? Are there any questions about this? Note that we aren't looking at any random allocations or anything here. We're going to compare a deterministic allocation against the deterministic share value. The random bundle xi is just used to find the share value, the deterministic share value. So let's look at an alternate interpretation of quantile shares as veto lists to provide some more motivation. So here's another process you can think about. An allocator who doesn't know the valuations is going to use the following procedure. Every agent submits a veto list of allocations of size at most L. Here, fairness is captured by the fact that L is the same for all of the agents. And the allocator will now select an allocation that is not in any of the veto lists. So looking at this example, you now have Alice and Bob, and they have these 3 items: the desk, chair, and laptop that they want to divide. And there are 8 allocations, right? So suppose L is now 3, and each of them is allowed to veto 3 allocations. So Alice vetoes these 3 allocations, Bob vetoes these 3 allocations. 2 allocations survive, and the allocator is free to pick any surviving allocation, and that's the one you're going to use. So now the question we ask is, how large can L be, the size of each agent's veto list, such that the allocator's task is always possible, such that there's always a surviving allocation? So in the absence of any other assumptions, with the picture that I drew, it seems trivial, right? So is it the number of allocations over n? Because in the worst case, the agents can veto disjoint sets of allocations. And if you allow each of them to veto the number of allocations over n, that can cover all the allocations and nothing survives this veto process. But that does not take into account the monotonicity of the agent's list. So if you enforce that the agent's veto lists are consistent, you get. So a list L is monotone consistent. If whenever an agent vetoes an allocation where it gets a bundle Si, it's also forced to veto all the allocations where it gets any Si prime subset of Si. If you do this, the question is now, how large can L be such that the allocator's task is always possible with monotone consistentness? And this is exactly equivalent to what we had on the previous slide. For what values of Q is the Q quantile share feasible for monotone valuation? So with that alternate motivation, we study this problem. We find an interesting connection with combinatorics. We show that it's in fact dependent on this conjecture, very famous conjecture in combinatorics called the Erdős matching conjecture. So what does this say? Given a K uniform hypergraph F, the matching number nu F is the size of the largest matching, or largest collection of pairwise disjoint sets in F. In this example, we have a 6 uniform hypergraph where every set has 6 elements, and it clearly has a matching of size 3. We can select these 3 sets from this family, and they have no pairwise overlap. So Erdős asks, how large in terms of the number of sets can a K uniform hypergraph on M vertices be if it has no n matching? This is sort of a question, a Ramsey type question in extremal combinatorics. So the conjecture is that for every value of M, K, and N, such that M is at least Kn, and for every family that does not have a matching of size n, so the matching number is less than n, we have that the size of the family is at most the maximum of some 2 expressions. Or in other words, if you take a family that is larger than this threshold, then you cannot avoid creating an n matching. For every family that is larger than this threshold, there is some n matching. That's the conjecture. If you're familiar with Ramsey theory, that's very similar to the Ramsey's theorem. It says that for every edge coloring, there is a kk, sufficiently large kn. So what is this expression? This is in fact the two simple hypergraphs that don't contain an n matching. The first one is all k element sets that contain at least one element of the first n minus 1 element. So if you only take sets that contain something, one of the first n minus 1 elements, this clearly has no n matching, because if you take n of these sets, they're going to overlap somewhere on the first n minus 1 element and can't form a matching. The other hypergraph is all k element subsets of the first kn minus 1 elements. Now again, if you take an n matching on a k element family, it has to have at least kn elements in total. So if you only take subsets of kn minus 1 elements, it has no n matching. The conjecture is that for all values of m, k, and n, one of these two is the extremal hypergraph, and there is no larger extremal hypergraph for any m, k, and n. What do we know about this conjecture? We know that it's true for small values of k and n. Some of these results were proved by Erdős himself, and some of the others are like the famous theorem of Erdős-Corrado. K equal to 3 was proved very recently. It's a long series of works, but this isn't super important. It's just to show that there's a lot of active research on this conjecture, and there are very small ranges for which the conjecture is still open. How do we connect this conjecture with quantile shares? So observe that the first thing to see is that the Q quantile share is feasible for on monotone valuations, if and only if it's feasible for monotone 0-1 valuation. Now, how do we see this? Just look at take a monotone valuation and arrange all of the bundles, starting with the empty bundle on the left and the full bundle on the right, in the order of the values. So you can take the Q quantile of this ordering and just set everything to the left to be value 0 and everything to the right to be value 1. This gives you a new 0-1 valuation function, for which now, if an allocation is Q fair with the new valuations, then it's giving everyone a 1 bundle, right? So it must be Q fair with the original valuations as well, because all the 1 bundles are on the right side of the threshold Q. So how do we connect the two problems now? You may be able to see some of this already. So you can see the ground set as the items, the hypergraph edges as the high valued bundles, or the 1 bundles in an agent's valuation function. And now taking an n matching is the same as saying you're giving every agent a one bundle or a high valued bundle. So what does the error matching conjecture tell us? If there is no way to give every agent a high valued bundle, a one bundle, that means there is no n matching in the hypergraph, which means there are not many one bundles according to the error matching conjecture. So if the number of one bundles is small, there are many zero bundles, and therefore the Q quantile is at 0 and not 1 for some value of Q. With that, what do we show? We show that the 1 over E quantile share is infeasible for all valuation classes. Notice that there's a constant quantile. We also show in the other direction that a constant quantile is feasible for monotone valuations if the error matching conjecture is true. So if the conjecture is true, we have the conditional result. The 1 over 2E quantile share is feasible for monotone valuation. And then final theorem is we show that for a bunch of structured valuation classes, some unconditional feasibility results don't depend on any conjecture. So for additive valuations, we in fact connect quantile shares with fairness by comparison in a really nice way. Any EF1 allocation is 0.14 over E fair. And for unit demand and make-for-rank valuations, we solve the problem exactly. We show that 1 over E is in fact the critical threshold. And we conjecture 1 over E is the critical threshold, matching the upper bound for monotone valuations and for all of its subclasses. So there's a lot of excitement about our definition. The first is because it's likely that it's feasible for monotone valuations and uncovers the correct way to measure fairness for monotone valuations. But more importantly, similar to EF1, which is fair for monotone, EF1, which exists for monotone valuations, this begins a new major research problem. So you know that the Q quantile share is feasible for constant values of Q for monotone valuations. Can you combine this with other desirable properties? So you can ask hundreds of questions along these lines and try to get results for monotone valuations with quantile fairness. All right, I just have one last two-slide thing I'm going to talk about, which is the job scheduling problem. You may be familiar with this. Here you have a set of jobs n that must be scheduled on a connection of machines, and every machine job pair has an associated running time Cij. Right. So the main objective here is to minimize the make span, where the make span of A is the maximum over the sum of the costs. So maximum Ci of Aj. So every agent has an additive running time. If a machine has to do 5 jobs, the total running time of the machine is the sum of the running times of the jobs. And you can, this is a, so trying to find mechanisms for job scheduling is a very famous problem. So with the small make span, these problems are of very great importance. This actually was first asked by Nissan and Ronin, and they conjectured that there is no truthful mechanism for job scheduling whose make span is less than n times the optimal, where n is the number of machines. And this actually led to the creation of the whole algorithmic mechanism design field of research, which has now led to tens of thousands of papers in the last 25 years. And also their conjecture, which started the whole field, was solved last year by Christodoulou, Koutsoupias, and Kovacs. But we can ask some additional properties. Instead of finding truthful mechanisms with small make span, you can also try to get rid of truthfulness and try to find fair mechanisms with small make span. So we can interpret the scheduling problem as a fair division problem. You can have the machines are the agents, the jobs are the chores or the badges, and the running times are the cost functions. So does there exist an assignment of jobs to machines that is fair for the machines, along with payments to the machines? That's the question we want to ask. This was first asked. Yeah, so natural question is there a fair low make span mechanism for job scheduling? And it turns out that the answer is no for NV freeness. So recall that we have the known characterization that an allocation is NV freeable if and only if it's locally efficient. So this was shown about 14 years ago now by Cohen, Feldman, Fiat, Kaplan, and Olnetsky. They showed that no NV free mechanism has make span less than omega of log m over log m times the optimal. But this still leaves open this question for other fairness notions. And we show that for proportional mechanisms, we can define a similar characterization as the NV free if and only if locally efficient thing that we saw earlier. There is a similar characterization which says an allocation is proportional, is proportionable, can be made proportional with payments if and only if it is what we call mean efficient. So its total cost is at most some threshold cost. And then we show that there is a proportional mechanism for job scheduling with make span 3 over 2 times the optimal, and this is stacked. So this is only a constant factor loss over the optimal make span. I'm not going to get into too much detail about our mechanism, but yeah, we can also combine it with the 2 approximation for make span minimization to get a polytime mechanism. So there's still many open questions of proportional job scheduling. So those are the 4 papers I wanted to talk about. Some immediate future work for me, and if any of you are interested that you can look into, are for all of these problems, we leave some open problems. So for the subsidies, I told you For monotone valuations, there's still a gap between n-1 and n squared. But you can also ask about fairness via subsidy beyond item allocation. For example, job sharing that I spoke about, but also for voting and a lot of other problems. For randomization, we showed that there is a randomization of NV cycles that is 1/2 EF in expectation. So does there exist a randomization that is in fact ex ante NV free? This is open. For quantiles, can you prove the error dispatching conjecture? Big open problem, of course. But also, can you prove that the conjecture is true up to a constant factor? As far as we know, nobody has looked at this question. So this was not a very meaningful question before our work, right? Proving that an extremal combinatorics conjecture is true up to some multiplicative constant factor doesn't have any meaning, but now it actually implies something in fair division. So this is an interesting question you might think about. And for scheduling, we saw that NV-free scheduling with small makespan is impossible, and that proportional scheduling is possible, and we show that. This still leaves open the question of relaxations of NV-freeness, like alpha EF or EF1. Finally, I want to step back. My last slide is about more generally on the current and future of fair division. This is a very popular research area with many huge questions that you'd think have been asked like 50 years ago, but somehow they've been only recently posed in the last 5 or 10 years. And also after 2020, this is becoming bigger. So there are many publications at many top theory conferences, but also AI conferences and EconCS conferences, of course. And it's receiving increasing recognition. There's many best paper awards that people have got. There's a prominent member of our field who has many career awards for his work in fair division. And there are many tutorials, workshops, and surveys in the last 3 or 4 years in a lot of venues. And also, fair division has many, many extensions that haven't been explored. So I spoke about some work in theory and combinatorics, but you can also think about other questions in economics, like approval voting and participatory budgeting, and many questions in, for example, in AI with fair classification, proportional clustering, fair array learning, etc. That's the end of my talk. Thank you. Yeah, so you have, in the scheduling problem, you have machines, you have jobs, you want to schedule the jobs to the machines, and the machines incur a cost. You can also make payments either between the machines or pay a machine for taking on some jobs. And this gives you a natural definition of envy freeness between the machines. So a machine is going to envy another agent if the cost of that other agent's bundle minus the other agent's payment is smaller than that machine's cost minus payment. You're adding some payments and you're adding the constraint that you want the final allocation to be envy free. If you do this, you necessarily incur a huge increase in the minimum make span. That was shown in earlier work. What we show is if you change the fairness definition to proportionality, you incur only a 3/2 factor loss in the optimal make span, and this is tight. And the question of relaxed envy freeness, like approximate envy freeness in the multiplicative sense, alpha EF, or EF1 or EFX for this same job scheduling thing, those questions are open. And we looked at them for a very long time. They're very hard, but they make a lot of sense. So it's possible that there exists a mechanism that for job scheduling that finds an EF1 allocation of the jobs to the machines with a constant factor loss in the optimal make span. This is an open question. Yeah. Thanks. Oh, thank you very much. Vishnu.